Today, we're zooming in on perovskite solar cells. We're going to travel from microscopic crystal flaws all the way up to massive clean energy breakthroughs. If you want to understand exactly how the materials of the future actually work on a molecular level, well, you are absolutely in the right place. But first, we really have to address a massive elephant in the room. What is actually keeping the next generation of super efficient solar panels off your roof right now? Perovskites are incredibly promising. They're cheap to make and have incredible light-absorbing properties. But they have a fatal microscopic flaw, a vulnerability so tiny, yet so destructive that it threatens to derail the whole technology. Today, we're going to explore exactly what that flaw is, and more importantly, the brilliant chemical engineering used to fix it.
Okay, here's our roadmap for today. 1. The perovskite defect problem. 2. What is passivation? 3. Where did defects hide? 4. Mechanisms, the microscopic fix. And 5. Real-world solar performance.
All right, Section 1, the perovskite defect problem.
To understand the fix, we really have to understand the flaw. Perovskites are, quite frankly, the divas of the solar world. They're highly sensitive materials that degrade when exposed to moisture, oxygen, and heat. But their biggest problems start before they ever even see the sun, right inside their own crystal structure. Look at this comparison here. In an ideal scenario, sunlight hits the perovskite, knocking electrons loose. These photogenerated electrons and holes travel smoothly to the electrodes to generate electricity. Beautiful, right? But in reality, the perovskite film forms with defects. These defects act like microscopic potholes or trap states. Instead of producing electricity, electrons and holes fall into these potholes, annihilate each other, and the energy is lost entirely as heat. This is known as non-radiative recombination, and it is the ultimate enemy of efficiency.
Let's really get into the details here, because the specific nature of these defects is fascinating. A typical perovskite crystal consists of a very specific arrangement of ions. But during crystallization, things go wrong. A halide vacancy, for example, is literally a missing iodide ion. It creates a trap state and actually allows other ions to migrate dangerously through the material. Then we have lead vacancies, which cause rapid charge recombination. And critically, on the surface, we find undercoordinated lead-2+ atoms. Because their neighboring iodide ions are just missing, these surface atoms act as incredibly strong electron traps right within the electronic band gap of the material. They literally swallow your solar power.
Moving on to Section 2, what is passivation? So if defects are the microscopic potholes, passivation is the molecular asphalt we use to pave right over them. By definition, it's the process of reducing defects in the perovskite material and at its interfaces to neutralize trap states, improving both efficiency and long-term stability. And listen, this isn't just a minor tweak. This is the absolutely fundamental strategy in all modern perovskite solar cell engineering. Without this, the technology simply does not work long-term. Let's see how this actually impacts device performance. Without passivation, those trap states severely lower the carrier lifetime and the open circuit voltage of the solar cell. You get lower current and terrible stability. But with passivation, we chemically neutralize those defects. The traps are filled, electrons and holes can now move freely, charge extraction becomes highly efficient, and the energy actually makes it out of the solar cell to power your devices. Section 3. Where do defects hide? The trick is, these microscopic defects are everywhere, and we need specific chemical agents for each zone. Surface defects on the very top of the perovskite are incredibly common because of dangling bonds, so we use materials like PEAI or FAI to heal them. But defects also hide deep within the film at the green boundaries. These are disordered crystal regions where we use polymers like PMMA to fill the gaps. Then there are bulk defects throughout the entire crystal, which we target by mixing alkali metals like potassium iodide right into the precursor liquid. Finally, at the interfaces where the perovskite actually meets the transport layers, we use ultrathin oxides or self-assembled monolayers. It's essentially a highly targeted, multi-front chemical war. To make this tangible, let's walk through how this is actually done in the lab for surface passivation. It's remarkably elegant. First, you deposit and heat, or anneal, your perovskite film. Then you prepare a highly dilute passivation solution, just 1 to 10 milligrams per milliliter. You drop this onto the spinning perovskite for 20 to 40 seconds, a process called spin coating. Finally, you bake it at 80 to 100 degrees Celsius for just a few minutes. This incredibly simple, low-cost process creates a chemical passivation layer that is only a few nanometers thick, yet it completely transforms the material. Now for Section 4, Mechanisms, the microscopic fix.
We are going into the detailed chemistry now to see exactly how these molecules fight back on a quantum level. The most common mechanism is chemical coordination, specifically a Lewis acid-base interaction. Remember those under-coordinated lead 2+ atoms sitting on the surface with missing iodides? Well, they are desperate for electrons. So we introduce a Lewis base, a molecule like pyridine or thiourea. These molecules possess a lone pair of electrons. The Lewis base just donates its lone pair to the lead atom, forming a coordinate bond. By satisfying the lead atom's need for electrons, the electronic trap state simply vanishes. The pothole is chemically filled.
Another brilliant tactic is direct vacancy filling. Missing iodide ions are one of the most common defects, creating literal empty spaces right in the crystal lattice. If we apply passivation molecules that contain iodide themselves, like PEAI or potassium iodide, they act like a microscopic delivery service. They supply the extra iodide ions needed to physically plug those empty vacancies. And not only does this eliminate the trap state, but it actively stops other ions from migrating through the empty spaces, which vastly reduces performance hysteresis and improves the cell's overall stability.
Then we have the creation of a 2D perovskite layer. When we use large organic ammonium salts, again, like PEAI, they're actually too bulky to squeeze inside the 3D perovskite crystal lattice, so instead, they react only with the top surface. They basically assemble into a thin, two-dimensional layer sitting right on top of the 3D material. Think of this as literal molecular armor. It physically blocks moisture from penetrating the cell while simultaneously passivating the surface defects right beneath it.
And there are even more tactics in this microscopic toolkit. We use polymers for grain boundary filling to occupy empty spaces and prevent moisture penetration deep inside the film. We use ultra-thin inorganic layers for interface passivation to smooth out the boundaries between materials. And fascinatingly, we use electrostatic passivation. Certain molecules in self-assembled monolayers, or SAMs, have permanent dipoles. Just by being there, their electric fields shift the local vacuum level, perfectly aligning the energy levels of the different materials so electrons can glide right out of the solar cell with zero resistance.
Section 5. Real-world solar performance.
We've looked at the microscopic chemistry, but let's zoom out for a second. Why do all these intricate nanometer scale details actually matter for our clean energy future? Well, they matter because of this number right here, 26%. Thanks to the advanced passivation strategies we've just detailed, state-of-the-art single-junction perovskite cells now exceed 26% power conversion efficiency. To put that into perspective, that is an incredible mark that rivals or beats traditional silicon solar panels that have been in development for literally decades. Passivation is the absolute key that unlocked this milestone.
Let's look at exactly how that efficiency skyrockets mathematically. When we lower the trap density, the carrier lifetime of the electrons becomes much longer because there is less non-radiative recombination. This directly results in a higher open circuit voltage, driven by a larger quasi-Fermi level splitting. Furthermore, because fewer traps impede the carriers, the short circuit current and the fill factor also increase. When you multiply those higher voltages and higher currents together, your overall power conversion efficiency jumps from mediocre to world record breaking.
But efficiency doesn't really matter if the panel breaks in a week. Remember how we called perovskites divas? Passivation solves the diva problem. That 2D molecular armor acts as a hydrophobic barrier, drastically reducing water penetration. The chemical layers slow oxygen diffusion, preventing the materials from oxidizing. By eliminating vacancies, we immobilize mobile ions that would otherwise degrade the cell under sunlight. And it even physically stabilizes the crystal lattice against thermal stress. Passivation gives these materials the tough operational stability they desperately need to survive heat, light, and humidity in the harsh real world.
To bring it all together, let's look at this definitive summary straight from the source material. The central purpose of passivation is to remove or neutralize defect-induced trap states and stabilize vulnerable regions of the perovskite. That is the absolute linchpin of this entire technology. By mastering the chemistry of missing atoms and microscopic pothole filling, we take a fragile crystal and turn it into a durable, hyper-efficient energy powerhouse.
Which leaves us with one final thrilling question. Is this invisible molecular armor the final key to powering the entire globe with cheap, printable solar energy? The breakthroughs are happening at just a breathtaking pace, and as we continue to perfect these nanoscale chemical fixes, a truly clean energy future looks brighter than ever. Thank you so much for joining me on this deep dive. Keep exploring, keep learning, and I'll catch you on the next explainer.